Great, today's pre-cal lecture is 7.6, and this is the Gauss-Jordan method of solving linear equations. So 7.6.1. Using the Gauss-Jordan method, to solve linear equations. All right, the Gauss-Jordan method is just simply a way of using matrices as a shortcut using the elimination method to solve a system of equations. We're only going to go through two equations and two unknowns with this method, but if you get good at it, it's really a fast way to do elimination. And so the rules are with the Gauss-Jordan method, you may flip the order of rows. You may multiply a row by a constant, just like in elimination. And you can replace a row by the sum or difference of two rows. So just like with elimination equations, all right, you're going to add, you're going to subtract rows to try to eliminate a variable. All right, it's just a shortcut method. So the goal, so we're going to work with these matrices, and we want to get something that looks like this: 1, 0, and then some constant. And that constant will be the value for x. And then 0, 1, and some constant. So we're going to work with our matrix until we can get something like this. And it's okay if the top is 0, 1, and the bottom is 1, 0. Okay, but this is the x column. This is the y column. So when you get 1 in the x column, go ahead and label that like that. When you get 1 in the x column, a 0 in the y column, and a constant, that constant's the value of x. When you get a 0 in the x column and a 1 in the y column, that constant is the value of y. All right, so I'm going to let you pause the video and make sure that you've copied all this down, and then we'll go ahead and start two examples with the Gauss-Jordan method. All right, our first example is to solve this system. X plus y is equal to 5, and x minus y is equal to -1. So that'd be a pretty easy system to solve with substitution, but I want to start out with a fairly easy example. So we're going to turn this system into a matrix. Okay, so we've got in the x column, we've got a 1, 1, and 5, for our first row, and then 1, negative 1, negative 1 for our second row. Just taking the coefficients in front of x, coefficients in front of y, and then the constants. Okay, so what I want in this top row is a 1, a 0, and something. So if I add row 1 and row 2, that's going to put a 0 right here. So I like to put the instruction right outside the row. So we're going to replace row 1 with row 1 plus row 2. Okay, if we do that, 1 plus 1 is 2, 1 plus negative 1 is 0, 5 plus negative 1 is 4, and then we're just going to recopy the second row. All right, now we're going to divide row 1 because we want a 1 here. We'll divide by 2. Right? When we divide 2 by 2, we get 1. 0 by 2 is 0. 4 by 2 is 2. And then we're just going to copy the second row. 1, negative 1, negative 1. So we have half our solution. The x value is 2. We have a 1 here, a 0 here. The x value is 2. So we can go ahead, I'll go ahead and write that up here. 2 something is our solution. All right, now I want to get a 0 right here. So I'm going to continue to use this 1, 0, 2, and I'll replace row 2 with row 1 minus row 2. Okay, because 1 minus 1 would give me my 0 here. Right, so when I do that, just going to recopy that first row, 1, 0, 2. And now the second row, 1 minus 1 is 0. 0 minus negative 1 is 1. And 2 minus negative 1 is 3. So now we have the matrix we want. The x value is 2. The y value, we have a 1 there, is 3. So the solution, you can check it if you want, to this system is 2, 3. The next example, I'm going to use kind of a shorthand to go a little bit faster. But you can go ahead and pause the video to write that down if you like. Okay, the next example we want to solve 3x minus 4y is equal to 1, and 5x plus 2y is equal to 19. So let's convert that into a matrix. And instead of going down, I'm going to try to go long ways this time. So we have 3, negative 4, 1, and 5, 2, 19. Okay, I can see an opening here that if I were to multiply the second row by 2 and then add it to the first row, I could get a 0. Okay, so let's multiply. So instead of writing it all out, I'm just going to put a times 2. Okay, and that's going to give me, we're going to go 3, negative 4, 1, 10, 4, and 38. Okay, so I want to get a a 0 here in this, either one. So I'm going to replace row 1 with row 1 plus row 2. And that's going to give me a 0 right here. Okay, row 1 plus row 2 will have 13. Negative 4 and 4 is 0. 1 plus 38 is 39. I'll just copy the bottom row again. 10, 4, 38. Now that I have my 0 in the y column, it's easy to solve for x. We're going to divide that entire row by 13. That'll give me my 1 here. So I've got 1, 0, and 39 divided by 13 will be 3. So we know that the x value of the solution is 3. We're going to recopy the second row. 10, 4, 38. Okay, so for my solution, I've already got half of it. We know we've got a 3. Okay, I'm going to recopy that matrix down here so that I won't run out of room. So I've got a 1, 0, 3, 10, 4, 38. All right, so what I want to do is get a 0 right here. Okay, so I'm going to replace row 2 with row 2 minus 10 times row 1. Okay, 10 times row 1, then I'd have a 10 minus 10. So row 2 minus 10 times row 1. Okay, I'm just going to continue to keep that 1, 0, 3 there. 10 minus 10 is 0. 4 minus 10 times 0 is just 4. 38 minus 10 times 3, so 38 minus 30 is 8. Right? So now we're almost home. We could divide row 2 by 4. And then we have our solution. 1, 0, 3. 0 divided by 4 is 0. 4 divided by 4 is 1. 8 divided by 4 is 2. So we have our y value. In the y column we have a 1, and in the constant column we have a 2. So the solution for this second set of equations is 3, 2. So that concludes section 7.6, the Gauss-Jordan method. I'm going to step aside a second in case you need to pause the video, and then I will give you the solutions to homework 7.6. All right, for 7.6 homework assignment, number 1, the answer is 1, negative 3. Number 2, the answer is 2, negative 2. Number 3, we've got a fraction here, 1/11 and 5/11. And number 4, the answer is 2/5. 1/2. So please try to work those. Any that you can't get, I'd be happy to work for you when school reconvenes. So that concludes lecture 7.6.